This is Professor Mark Barkey at the University of Alabama. I'd like to talk a little bit about rainflow cycle counting in this video and in a couple of other videos that I'm going to make in this series, either a total of 2 or maybe 3 videos. But this one is just kind of an introduction to rainflow cycle counting. I'm going to explain why it's named the way it is, why it is needed, its relationship to uniaxial cyclic plasticity, and what you can do with it. Now, rainflow cycle counting is something that I teach in fatigue analysis, but I also teach this in my plasticity class. They're very much related to one another. So let's just start off with talking about what you can do with it, then we'll get into the details of why it's called rainflow cycle counting. It's kind of an unusual name. We'll see where that comes from, and some other issues to do with cycle counting. So, what is cycle counting? We have this idea in fatigue analysis that a cycle is a single damaging event. In order to have fatigue, you need to have reversals of load, and cycle counting is a way to count those reversals of load. So let's just kind of make that point right here. And then a cycle is a damaging event for fatigue. Now you might say, well, I know how to count cycles if I have a sine wave. I have load or stress versus time, and I'm starting up here. And I have this thing repeat. Well, it starts here, and then it's kind of over here again. So maybe this is one complete cycle, and then when I do this, this is another complete cycle. Well, for what's called fully reversed cyclic loading, it's very easy to determine the number of cycles. So this is a fully reversed. Or just any kind of sinusoidal type loading. In this case, cycles are very easy to identify. Now, I will say I apologize for my writing. I'm writing on a tablet that doesn't have a screen on it. The screen is on my computer, so I can't exactly see how things line up very well. So my writing is a little bit off. But for this sinusoidal type loading, cycles are easy to identify. But in other cases, particularly for variable amplitude loading, cycles are a lot harder to identify. So let me show an example of a variable amplitude loading history. All right, so here's a variable amplitude loading history that I've just sketched. And the sources of these variable amplitude loading histories are any kind of ground vehicle or aircraft or anything that has a lot of back and forth at different amplitudes and frequencies in it. So this is a plot that I have labeled here as stress versus time. It could be load, or it could be strain, or any kind of other type of quantity like that we want to count cycles on. But this particular history has a lot of small amplitudes, has a lot of larger amplitudes, and just by looking at it, it's really hard to say what might constitute cycles. So we could take some guesses, I suppose. We have it kind of starting here and well, here. So maybe down and up, maybe that's a cycle. But then we also have this thing happening again at different levels. We also have some things that are in here. So we might even say, well, here to here to here, maybe that's a cycle also. But we know we have some small cycles and some large cycles. There are different techniques for identifying cycles, but rainflow cycle counting is the only method for uniaxial loading that is guaranteed to identify all the cycles that you have in a loading history. Other techniques are level crossings and things like that. And historically they've been used, and they can still be used in certain special circumstances, but really rainflow cycle counting is what you need to use if you're going to do a fatigue analysis on a variable amplitude loading history. Okay, so again, rainflow cycle counting is the only technique able to identify all cycles in a uniaxial variable amplitude loading history. Now, the way that this relates to uniaxial cyclic plasticity has to do with the correlation of hysteresis loops to closed cycles. Okay, so let's kind of back off, and before we look at the complicated variable amplitude history, let's kind of look at a more simple constant amplitude history. If we have a time history, so you have stress versus time, where we had our sine wave. Maybe we start this at 0 and we go back and forth. If we were to plot the hysteresis response for that material, assuming that we have a little bit of plasticity, so what I mean by the hysteresis response is the stress versus strain curve, we have from 0 up to this maximum peak right here some initial loading. And we know that initial loading would be calculated by our monotonic stress strain curve. So that would be this dashed line that I have up here. Now hopefully you've been able to watch the videos I have on the massing hypothesis and everything for cyclic stress strain behavior. But what happens after this, from this point down to this bottom point, is we follow the hysteresis branch equation. And that I'm going to draw in as a solid line, where we have a certain elastic unloading range, then we start to have some plasticity, and then we go back up to the highest peak again. We have some elastic unloading from compression, then we have some plasticity, and it joins this point right here. And if we have a cyclically stable material, each time we do this and have another cycle, we are just having another set of branches that lie over the top of each other. And the takeaway from this is that each closed hysteresis loop represents a cycle. So cycle counting can, instead of looking at it in terms of stress versus time, if we think of it as stress versus strain, then each time we have that closed cycle, we have a damaging event, that closed hysteresis loop, and then we can calculate our fatigue damage based on either the stress range or the strain range of that particular hysteresis loop. And in fatigue analysis, you would use your appropriate damage parameter to figure out what the number of reversals or the number of cycles were for that particular event, and then calculate the number of damage, and then you accumulate damage and so forth. For now, we're just mainly focused on being able to identify those cycles. So let's take a look at what happens with a very simple variable amplitude loading history. So again, I have stress versus time here, and I'm going to plot the hysteresis response for the material, assuming that we have a little bit of plasticity. Now, I'm doing this as a sketch, but the sketch is good enough to identify these closed hysteresis loops. So over on this panel, I'm going to have my sigma and my epsilon, my stress versus strain. And this dotted line right here to take us up to this first value is going to be our uniaxial stress strain curve. And again, a little bit of plasticity. I'm just indicating that with this curve bending over a little bit, so I'm at this point right here. And first we're going to go down to some value right here. Maybe we have some elastic behavior here, and then it starts to curve over a little bit. And so let's call this point A, maybe this point B. Maybe this is point C, and then I go up a little bit. And That's maybe almost all elastic, or pretty close to it. Let's put just a tiny bit of plasticity in here. And then this is point C. And then we go all the way down to this point D. And on our way down to point D, remember what happens in cyclic plasticity. First we close off this excursion from B to C. And then from this point here downward to point D, we follow this branch of the hysteresis curve. So it's as if this did not happen at all. So we're here at point D. And then from point D, we go all the way back up to this point A. And I'm indicating this at the same level. So something that we'll see with ASTM definition of rainflow cycle counting is that we always start and end with our highest stress level. Okay, so if we look at this, we have one big cycle and we have one small cycle right here. So I'll label this one delta sigma A to D, and this one is a delta sigma from B to C. Now we can take those particular stress ranges and we can plug those into our damage parameter or look at our stress life curve if we're using that approach. We can find out how much damage each of those closed cycles account for. Alright, so with this variable amplitude loading, the thing to remember is the material has what's called hysteresis or memory. At this point that we have at point B, it has remembered that really this branch started at A and we complete the branch from B to D as if starting with this tip at point A. Let's try another one that's maybe a little bit more complicated, and I'll sketch this out. And we'll do stress versus time here. And again, let's kind of start out maybe very similar. We'll go to some point here, and maybe we'll have a few different cycles. Again, we're starting and we're ending at the same level of stress. Alright, let's see if we can work this out. Sometimes these are hard to sketch when they get to have a bunch of little bitty cycles in here, but we're just going to do the best that we can. Alright, so monotonic from here to our first point. Try to make this kind of with a bunch of plasticity so we can open this up a little bit. So now this is our point A. We're going to go down to point B. Here we go to C. And then back down to D. Now, C back to B is one loop, and then we're going to continue on from B to D. So we've identified a closed loop right here. And now we're at D. We're going to go up. We're not going to go all the way up to A. Okay, so I guess that would be point E. And then we're going to go down to F. And on our way back down, we close off point the loop from E to D. And I know these are kind of hard to sketch. And then E, we're going all the way down to F, way down here. So we close off this branch from E to F, and then we follow along this curve as if all this other stuff never happened. We're starting our tip at A, and we're going all the way down to F. Alright, we go F to G, G to H, let's see, now H doesn't go all the way down to F, so let me fix this up a little bit. And we're going to go back up to A right here. So on the way back from H back up to A, I first close off this loop So I have a delta sigma GH, and now when I complete this branch, I go all the way back up to A, and I complete the big loop, which is from A to F. Alright, so now I have, let's see, 1, 2, 3, 4 closed hysteresis loops in that variable amplitude loading history. Now where things get interesting is when you have multiple nested loops. Let me see if I can draw an example of that. Alright, so let's take a look at this one. We have from zero stress and strain up using a monotonic curve to point A, and then we use our cyclic stress strain curve from A to B, and so forth. Let's sketch the hysteresis response. In this case, and again I'm going to exaggerate the plasticity in here. So maybe this is our point A, and we're going all the way down here to point B. And then we go up to point C, back down to point D, to E, to F. Right now we have no closed loops. And now we go all the way from F back up to G, which is the same level as A. Now, here's where it gets interesting. From F, we go and we close the loop from F to E on this hysteresis loop. Then we close the branch from D to C, using D as the tip. And then we close the portion of the branch from C all the way to A, using point B as the tip. And now we end up with a stress range of EF, a stress range of, what do we have here, CD, and then a stress range from A to B. We have 3 closed hysteresis loops. Let me see, maybe I'll use a different color. 1, 2, and then the big one, number 3. Alright, so with this you kind of see what the rules are. You have to remember some of these points from time to time. We're going to formalize this into an algorithm, and eventually I'll show you a computer code that I've written in Fortran that will do rainflow cycle counting. But at this point, if you want some practice, try sketching your own time histories and doing hysteresis plots, assuming a little bit of plasticity. If you know the actual material properties, you can even calculate these hysteresis plots. If we use the Ramberg-Osgood equation, and the K and the N, we can go through all of that and figure out the exact values for the stress and strain at each of these tips. Now the interesting thing for rainflow cycle counting is that we never have to calculate strain. It all can be operated on with just our one variable, our active time history of stress, sigma, or whatever active history you have. So rainflow cycle counting can be done on stress, strain, time, temperature, whatever. We're only looking at the change in the ups and downs of that one variable with respect to time, but we have this equivalence to finding these closed hysteresis loops on our stress strain plot. So what we'll do to demonstrate our algorithm is we'll kind of look at this variable. This variable goes down, then it goes up some, then it comes back down some more, and then it goes back up some more, and then it goes back down, and then it goes up, and on the way it closes off all these different other loops. Okay, so we have A to B to A. We have a loop here, C, D, C. We have this loop E, F. Okay, so we have those 3 hysteresis loops. This portion here and this portion here combined to give us our A, B, a loop. Okay. So we're going to take a look at this from a I prefer to develop a rainflow cycle counting algorithm in terms of logic, looking at the time history. But the reason why it's called rainflow cycle counting is if you were to take this time history, sigma versus time, and rotate it by 90 degrees, maybe I can make a copy of that and show you here. The original developer of rainflow cycle counting was a Japanese researcher in fatigue analysis, Endo. And if you were to imagine rain flowing off of a pagoda roof, the rain would start here and it would drip to this point and then come down and then continue on, and then the rain from here maybe would drip at this point and come down and so forth. You can get an equivalence to being able to identify closed hysteresis loops by how a rain drops off of various levels of a pagoda. Now again, I prefer personally a little bit different approach of thinking about it, more from the perspective of hysteresis loops. That's because I teach this class in plasticity, and it seems to make a lot of sense to me to think of it that way. But again, we have to understand that we're looking for what will create closed hysteresis loops, yet at the same time we have to remember these different points on our hysteresis branch so we can complete these hysteresis branches to get these hysteresis loops identified. Now there's one other thing I want to talk about in this video, and that is something called rainflow with mean, or a from-to rainflow matrix. Let me start with a clean page here. All right, suppose we did our analysis, and on our stress-strain plot we found 3 closed hysteresis loops on our variable amplitude loading history. We have one overall hysteresis loop, and it goes from a stress level sigma. It goes from 100 to minus 200, and then back to 100. That's kind of implied. We have another one that goes from 75 to minus 20, and then we have another one that goes from, it starts at minus 50 and it goes to 15. And these are all, you can say, megapascal units if you like. Okay, so these are my identified cycles. So if I have a lot of these happening in a huge variable amplitude history, I can construct what's called a from-to rainflow matrix. All right, so what that means is if I have a column here that says from and another one here that says to, if you can think of a grid, and this was, let me put some numbers here. I'll pause the video for a second. Alright, so I decided to make a quick one with Excel. So here's a chart here, and on the top is the stress level where I'm going from, and on the side it's the stress level where I'm going to. So this first one is 100 to minus 200. So we have 100, I'm going from 100 down to minus 200. So I put one tick mark here, and then, you know, if I have 500 counts, I put 500 here. And then I'm going 75 to minus 20. Okay, so plus 75, well, it's kind of an odd one, I guess, because we're kind of in between this bin and this bin. So maybe, let's see, from 0 to 50 we go here, maybe from 50 to 100 we go here, and this is 100 and greater. So maybe we're put a count in this bin from 75 to minus 20. Minus 20 would be in this bin right here. So we have a count in this bin, and then we're going from minus 50 to positive 15. So we go minus 50 to plus positive 15. So maybe we would have a count in this spot right here. So this is called a from to rainflow matrix. These are used sometimes, and it's a way to reduce a very lengthy time history that has a lot of variable amplitude cycles in it into a very kind of single page description of that time history. You can even reproduce time histories with this kind of data. You just need to make sure you have from and to. Now, what is lost in this are any possible sequence effects that you might have. So with any kind of data reduction technique, if you reduce the amount of data that you have, you're also losing some information. But if you get really good at these, if you work in a particular field, you can take a look at these from to rainflow matrices, and you can get a very good feel for that time history. Now, some people will do these in like different sized bins. They will do this in kind of a 3D plot. There's different software options. This is kind of the basic idea with the from to matrix. There's another type of matrix that's often used in rainflow cycle counting, and that's called a rainflow with mean matrix. So let me describe that. We can use our same data that we have here as well. Okay, so here's a setup of a matrix that's in a range mean format. And I've calculated the mean and the range of each of these. So we have a range of 300 with a mean of minus 50. So we would have a count in this spot. We have a range of 95 with a mean of 27.5. So a range of 95 and a mean of positive 27.5. So maybe we're in this spot with a count. And then we have a range of 65 with a mean of 17.5. So maybe we would end up with a count in this spot. All right, and so in this way, you can also build up these rainflow with mean matrices. If you want to find some examples of rainflow matrices, take a look at various SAE publications. The one I would recommend is this one, Multi-Axial Fatigue Analysis and Experiments. It goes back to 1989. It's published by the Society of Automotive Engineers, and it's AE14. All right. In modern usage, now 1989 was a while back, in modern usage of computers, it's not a big deal to store a lot of information, but it still is a very nice way to graphically show kind of the nature of the time history that you have. So for example, if you end up with several thousand counts in this range that are very low level with no mean, and maybe a few outliers, then that gives you an idea of the nature of your time history that you're dealing with. If you do enough fatigue analysis, then again you get a kind of a feel for where your damaging events are occurring in the matrix, and the relative magnitude of the counts in those different bins gives you an idea of how much that damage should be weighted. Alright, so what we've done is we've talked a little bit about rainflow cycle counting. We've related this to uniaxial cyclic plasticity. We've talked about rainflow matrices from and to and range mean. And what we're going to do next then in the next video is we're going to take a look very carefully at identifying some rules that we can use to write our own rainflow cycle counting algorithm.